So in our day 3 of our 5-day look at relativity, we're going to get into electricity and magnetism. Now we know that it was Maxwell's equations that were the driving force behind electricity and magnetism. And Maxwell's equations allow us to do pretty much anything with electricity and magnetism, but they seem to be incompatible with Newtonian mechanics. So now that we've seen that Newtonian mechanics were the flaw, to really understand what's going on, we need to dig into Maxwell's equations further. And the first way, or the first piece of information we need to do that is know how to multiply vectors. We have been dealing with vectors so far. We've never had to multiply them. For example, if you have two vectors, A and B, how can you multiply them? We've got 3 components. There's x, y, and z components in each. There's magnitude and direction. If they were just magnitudes, multiplying wouldn't be hard, but how do we multiply something with directions? Turns out there's actually 2 ways to do it. There's a dot product, and there is the cross product. The dot product gives us an answer that's a scalar, not a vector. The cross product does produce a vector. Now, some of these we have already seen. So when we talk about the work done on an object, it's the product of the force and the distance traveled parallel to that force. Well, that's actually shorthand. What we really have there is the force and the dot product with the distance. This will produce the force and the parallel distance because that's actually equal to just the magnitude of F times the magnitude of D times the sine of the angle between them. Another way to work with it, which in the real world is a little more convenient because we generally treat our vectors by components and we don't break them out into the angles like we do in high school. Well, that's fx dx plus fy dy plus fz dz. So we're just taking the product of the x components, the product of the y components, the product of the z components, and we're adding those products together. So that's any scalar. So if you have the vector A dot product with the vector B, you get ax bx plus ay by plus az bz, which is equal to magnitude of A times the magnitude of B times the sine of the angle between them. You'll be able to prove this is true in first-year university linear algebra courses. Now, the other type of product is the one that comes out with a vector. If we think back to our formula sheets, if the dot product ends up with parallel components, do we have any formulas for vector quantities where we multiply 2 vectors and get a vector out and they're dealing with perpendicular components? Well, there's at least one in the electricity and magnetism unit. The magnetic force acting on a charged particle moving through a magnetic field is the charge times the perpendicular component of velocity cross product with the magnetic field. So this will produce the force as a vector that is at right angles or perpendicular to both the velocity and the magnetic field. Now, this also has an expression similar to these for the dot product. Some of it is fairly easy to do. It's also, magnitude of V times magnitude of B, but this time times the cosine of the angle between them. Remember, cosine is maximum when the angle is 0. So in sine, if they're in the same direction, that's backwards. This is the cosine. This is the sine. Because we want this maximum when they are perpendicular, and we want the dot product maximum when they are parallel. My apologies. The cosine goes up here, and the sine goes down here. So now, what's the other way? Do we have an x and y version? We do. We're going to introduce the idea of having directional vectors. So if we have A, we could write that as components AX, BX, or sorry, AX, AY, and AZ. So our X, Y, and Z components. Let me just clean that up a bit. So we can write it as 3 components just in a column. So if F is Q, V, and B, well, can we write that in components somehow? We can. Rather than have all the Q's and V's and B's floating around, I will do the general case of A cross B first. So the cross product of A and B, the X component is going to be AYBZ minus AZBY. So the X component is not at all related to the X components of A and B. This is one of the ways we guarantee it's perpendicular. If we only have an X component for A, that's non-zero. And so if we have a 1, 0, 0 cross product with 0, 0, 1, well, if it's going to be perpendicular, we need to have either 0, 1, 0 or something. It doesn't necessarily need to be 1, but we need to make sure everything is in the Y component if it's going to be perpendicular to both X and Z. So we will actually see ourselves cycle through these variables. So the Y component is based on the X and Z components of the original, and the Z component of the product is based on the X and Y components of the original. And this is another one that you will be able to show is equal to the product of these two times sine once you get through that linear algebra course I mentioned before. So we are now armed with the tools we need to multiply vectors. There's one other tool that is going to be mostly familiar or more familiar to the calculus students, and that is the vector differential operator nabla. So that is nabla, N-A-B-L-A. So this has no value on its own. It's actually an operator. The d's and the dx, the dy, these won't make a lot of sense if you don't have the context of calculus. Just bear with me. But this is a vector operator where the x component will find the slope of something in the x direction, the y component will find the slope in the y direction, the z component will find the slope in the z direction. What's most important is the way that they interact with fields, because we can take this as a product in 2 different ways. So if we take it as a vector product, this first one with the dot product is called the divergence, because it really measures how quickly this vector field diverges from the origin. This one is called the curl. It measures how much curl we have. So how much these vector lines curve around. So these are the interpretations that we need. now that we have these tools in place with divergence, with curl, and with vector multiplication, we are ready to dig into Maxwell's equations.